Welcome back my dear friends and dear students. Good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3 course, which is data analysis and decision making 3 course on the NPTEL MOOC series. And this total course duration, as you know, is for 12 weeks. The total contact number of hours for the 12-week course is 30 hours, which when split into number of lectures is 60, considering that each week you have 5 lectures, each lecture being for half an hour. And you have already completed 11 weeks, that means after each week you take an assignment. So, you already completed, by the time you are hearing this, you have already taken 11 assignments, that after the 12th one the whole course will end, and then you will be taking the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, in the last 2 lectures, which was the 54th and the 55th, I just drew many different type of diagrams in order to make you understand that considering that normality holds for the distribution, whether for the univariate case or for the multivariate case, it was easy to understand how the reliable surface would be, the overall area and the center of gravity or the center of the circle or for the ellipse, with the vertical area, the direction being from the major axis or the horizontal direction being the minor axis. You can find out how the value of alpha as it changes, how the loci on each and every point of the locus of the reliable solution changes, and based on that you can find out that what is your overall the area, which should be equal to alpha i's, depending on I as you change the level of reliability, and based on that you can find out the solution, and which is the best fit solution for the case when the constraints are reliable with a certain level of probability. And for the case when it is non-normal, I have mentioned that time and again that trying to find out the feasible region is by itself difficult, and also if the center of gravity or the mid or the center of that overall area is to be found out, then obviously you will use different type of simulation techniques, and one was the decoupled method, one is the single loop method, one is the double loop method, but I will only concentrate on the decoupled method and concentrate that how this can problem be tackled. So, this is the 12th week, which is the 56th lecture. So, here I will again repeat, you have the constraints Gj's and J is equal to 1 to m. Each of them is converted into probabilistic framework, the constraints, and these alpha suffix J's, J is equal to 1 to m are the constraints, and how they can be incorporated is what the diagrams I was basically trying to draw. So, we will consider the sequential optimization and reliability assessment method, which is the Soraa method. So, the central idea is to employ a series of cycles, different loops of trying to optimize the deterministic optimization in one end, as I have been mentioning time and again, in the x plane or the x space, and the reliability analysis to be done in the u space. The transformation basically happens when you basically use one of the transformation techniques, which is the Rosenblatt one, which we will consider. I will just write the equations without going to the details, where you convert from the x space, find out x star suffix 1, 2, 3, 4 depending on the stages of optimization, that x 1 star is mapped onto the u space, then you find the optimization the MPP point in the u space, again transform it back to the x space and continue in doing this. Now, this deterministic optimization which you do, all the deterministic optimization methods we know, whatever have been discussed, obviously I was not able to consider all the methodologies, but whatever you do would be done using the simple optimization techniques we all know, or all which can be built up by reading the books. And what is more important is the this reliability phase which are decoupled. So, that is why it is known as a decoupled method, where you decouple this deterministic one and the reliability analysis one. So, let me continue reading it. Both are decoupled from each other. The reliability assessment is only conducted after the deterministic optimization is done, and the idea is like this. You basically have the initial design. I will come to the flow process chart later on. So, generally the bullet points how you do the methodology. You basically design it, design the problem, design the optimization one, and you basically solve the deterministic optimization techniques as such. Once the deterministic optimization gives you some x star. Now, these x stars need not be scalar, they can be vectors also. Once these x stars are found out, you basically do the reliability analysis and find out the u stars, check the convergence. If it is not, again you basically formulate the new deterministic optimization by basically, so this will be u star and u double star. Once u star is optimized to u double star, find out the inverse transformation of u double star into the deterministic space or the x space, again optimize, find out x star the next stage, then again go back to the u space and continue doing this. In case if convergence is obtained, you report those values of u star and those values of x star, and your answer or your job is done. So, how you do the reliability analysis is most important, which we will consider now. So, these are the diagrams which I have already discussed, and they would be considered later on when we do the reliability analysis. This is for the case when the variances are same, normal case. This is the case when the normal distribution is true for both of them. I am drawing only in the 2 dimension one, where the variance of x 2 or in the y plane is more. This is the third diagram where the variance for the variable which is in the x direction and x 1 is more. And in this diagram, where we consider the last diagram which we also consider in the last class 55th lecture, where the distribution per se are non-normal. So, in trying to find out the best surface area or the overall region would be difficult. Now, let me come to the reliability assessment of most probable point approach or the methodology. So, the MPP method is based on and is characterized by the use of analytical techniques, solution techniques to find a particular point in the design space, which can be used to estimate the probability of a system and success, and then you will utilize that value of u star or u star 1, u star 2, whatever it is, in order to report that the optimization is being done on the u space. The formally defined is basically a coordinate system of independent and standardized normal vectors. Now, here it should be important that the u space, all the variables have been transformed into u1 to un, and all of them are orthogonal. So, why we are doing that? Let me consider this using the simple Rosenblatt transformation. So, I will basically mark it here. Or right, I would not be going into these diagrams immediately, but I will come and mark it accordingly. So, let me prepare a blank slide, so it is easy for me to draw. So, here I start off the case. Okay. Now, the background goes like this. You have any distribution for x's and you want to transform into standardized normal space, which is u. Now, what is the background for that? So, the background is we come to simple CDF or probability distribution, which is the cumulative distribution function. So, the story goes like this. Consider you have f of x univariate one, we will go in the multivariate case within few minutes, and x is on the real line. So, basically x is from minimum, some minimum to some maximum, which means if, and consider this is a continuous one, it will be same, the concept will be same if we consider the discrete case of x also. So, what it means, all the 4 properties for the CDF should hold. 4 properties, if you remember, I have done in DADM 1 is that the if A is less than equal to B, A and B are the events which consist of sum of the values of x's, then the probability of A, or consider it is as a subset, which means this is a monotonically increasing function. So, because probabilities cannot be 0, they can be in the sense they cannot be negative, sorry. So, if they are 0 or positive. So, any addition values of x's or realized value take, the CDF value will be increasing. Point 1. Number 2 is that from x min to x max limit, I will not use the word x max, it should be basically x only, sorry, limit x tending to x min, f of x would be 0, limit x min to x and x tending to x max, f of x is equal to 1. And the other one is that the concept of left continuity and right continuity holds. So, the first one, second one, third one are the left, and the left continuity, right continuity concepts, if holds, we will consider that to be a CDF function. Now, what is the beauty based on which we will proceed is this: the minimum value for the CDF is always 0, whatever the PDF is or whatever the PMF is, the maximum value is 1. So, if you have two particular random variables f of x and f of y, we are going to transform, and y is basically u here, which we will consider later on. The distributions diagrams would look like this, the CDF values. So, one is between 0 and 1, and consider the other one is also between 0 and 1. So, I am going to do a one-to-one transformation between these two, which means if I know x and I know this CDF value, I also try to find of a particular the same CDF value here, such that the value of x 1 which I have would be mapped on to y 1, provided this is true. And what is true? Let me mark it here. It is like this: x min whatever it is till x 1 f of x dx will be equal to, now should be equal to, because this is equal to alpha, this also should be equal to alpha, this is alpha, the overall area is equal to y min plus y 1. So, consider this PDF is g of y dy. So, we can say convincingly the values of x 1 and the values of y 1 should be such that the overall area covered by addition of all the properties from the minimum values to those corresponding values of x 1 or y 1 in whichever space they are should be exact equal. Now, this is what we are going to utilize in the Rosenblatt transformation, considering it is a multivariate distribution. What it does is that it fixes f of x at some value which is given, and then correspondingly, so this is f of x 1, x 1 is basically now a random variable of one dimension. What we want to find out is the value of x 2 given x 1 is fixed, we calculate the values and find it out. Given x 1 and x 2, we try to find out x 3 and proceed in this direction such that given the prior point, given the prior values, we know that what value would be fixed for x1, x2, x3 such that the transformation would be given that at a fixed value of x1 what is the value of x2, and we are purposefully trying to take the orthogonal values of such that no dependent structure is between x1 and x2. Given x1, x2 as orthogonal, we fix them, then try to find out x3 value such that x1, x2 are also already orthogonal, then we will basically try to find out the orthogonal transformation of x3. So, here when you are doing the orthogonal transformation, you are basically doing in the U space, which as said is the standard normal deviate, which are all orthogonal u1 to un. Then given x1, x2, x3 are all orthogonal, or consider u1, u2, u3 are all orthogonal, you try to find out u4 and proceed in this direction such that you are able to find out all the values of u. So, this is what it states. Formally defined, it is a coordinate system where they are independent, this is important, independent and standardized normal vectors. Normal vectors because all of the mean values is 0 and standard deviation is 1, such that the cumulative distribution values which you take for the multivariate case is exactly equal to the cumulative distribution in the value terms, the alpha value on the x space. So, let me again read it. So, this is a coordinate system of an independent and standardized normal vector u. U is a vector from u1 to un. Hence, transformation of the input variables from the x space to the u space is required and is possible. So, what we do is this. We basically try to follow two procedures. We take the value of beta or alpha, whatever I have been talking about, and we want basically try to minimize the orthogonal, the norm or the distance, subject to the case that if you remember we have taken g of x dp as less than equal to 0 and that value is given as alpha, which is actually beta we are considering here. So, we will try to minimize the distance covered of or the norm of the in the U space. So, U space are orthogonal unit vectors. So, if I consider in the 2 dimension case it will be a circle, in a 3 dimensional case you would basically be a sphere and hypersphere in the higher dimensions. So, based on the subject the 2 constraints, what I will do is like this, and these will be discussed in a diagram later on. First, we will basically try to find out the minimum of the u's corresponding to the fact that the first derivative of the u's for each and every u's which you have is 0, which means there can be 2 ways. One is have the boundary space and try to increase the circle, like try to increase the circle such that at the moment it touches the feasible region endpoints or the curve or one of the constraints, that will give me the minimum value of beta. Beta is basically the minimum distance, remember. So, beta can change such that the tangent point would give you the u star based on which we will basically proceed to do the optimization in the reliability space. That is method 1. Method 2 is that keep the circle fixed at a level of beta and try to shift the boundary such that the boundary the moment it touches. So, obviously, the feasible and infeasible regions points would be considered in such a way that the moment the boundary touches, the boundary is moving, the moment it touches the circle or the sphere or the hypersphere, that point which is tangent will give you the u star. So, this is basically the general procedure. The point where it touches the boundary, that circle or the sphere or the hypersphere, that will be the most probable point where the concept of the level of reliability would be maintained, and also it will give you the minimum point where we are able to achieve that, such that that is the optimum point in the U space, which can be transformed back to the X space to basically start off the next stage of the optimization. That means, first you do with the minimum values, if you remember mu suffix x, mu suffix p, that value when is obtained, it will basically proceed to the next level which we obtain from the U space. Again do the optimization based on the second set of iterations in the deterministic space, again do the Rosenblatt transformation as I have considered, and continue doing it in this way such that you basically achieve the optimality as discussed. So, now there are the two methods which I discussed. One, the circle radius increasing or the sphere's radius increasing or the hyper sphere's overall the volume increasing till it touches the feasible region at a particular point and the tangent point at u star, or else keep the the circle or the sphere or the hypersphere fixed and move the boundary of the feasible region till it is tangent. So, how these are achieved, I will just show it very simply in a diagram. I talked, now basically see the diagrams. I will show both the diagrams at the same time rather than showing one at a time and then discuss. So, now here it like looks. Remember, I am considering it is a circle, two dimensional variants are same. The first case, you basically have in the u space. So, you have basically transformed it in the u space, you have the origin. So, the origin is here, and this circle, if you remember, beta was the minimum of mod of the u space, which is the distance. You have basically, you want to minimize that. What you do is that you keep shifting the feasible region more inside. So, the area which was there, I will just draw it, if possible. If I have it here, I will just note it down. Yes. So, this area was there, this was the deterministic one. So, you are going inside, more inside the feasible region. So, this invisible region is basically now increasing, that means the feasible region is now shrinking. So, you start moving. So, these green arrows which are there, they give you the incremental step in which the invisible region increases and it goes more inside the feasible region. That means, the feasible region shrinks till the point is reached where it is tangent, and that tangent point which I mentioned is the MPP or the most probable point in the two dimensions case, which would be u1 star and u2 star in the first iteration. So, it gives you the invisible region for the case when you have GJs, which is the transform function which you have in the u space, and the feasible region now shrinks, it moves step by step, and these dotted lines which you see, you start with the red one, the dotted ones are as they expand or the feasible region decreases till it is tangent, and the points which you have, the coordinate system which you have in the two dimension one is u1 and u2, which are always orthogonal as I mentioned. So, this is the method which you have for the PMA method, which is the performance measure approach, where your main criteria is to minimize the function g of u, provided the mod of the distance for in the u space is beta. Beta is the level of probability which you have already defined by the decision maker. While in the reliability index approach, which is RIA, you just reverse in the sense you minimize the mod of the distance subject to the case that g of u or the functional transformation which you have done for g in the u space is kept at 0, because 0 is the basically, if you remember, is the boundary. In this case, it happens like this. You have the invisible region and feasible region is demarcated very clearly. Now, the circle with the point which is u1, u2 or the origin whatever it is there, it starts increasing like concentric circles. The moment the value of the minimization is approached, subject to the case when you have the region when it is exactly equal to 0, because the demarcation is that in the feasible region GJs for each and every constraints is greater than 0, in the infeasible region is less than 0. So, at the boundary it will be exactly equal to 0. The moment it basically increases and becomes a tangent at that point, the radius of that circle which will be beta, which we are trying to minimize. So, minimization on the mod is basically the radius, that will give you the level of reliability which we want to achieve based on the fact what has been given a priori, and the point where it will be minimum for the optimization case, which is minimization of the mod, would give you that u star which is the MPP point in u1 star and u2 star. So, in one case I am repeating, the boundary moves inside, that means the more inside the feasible region, moment it becomes tangent, you stop, report that values, and that point is the MPP, which would be again transformed back in the X space, and we will start the second iteration using the deterministic one. So, the first iteration was, I am again repeating it, based on the mean values of the X's and the P's, and then the second iteration will start, you will get an answer, you will again do the Rosenblatt transformation, come into the U space, and again do either the PMA or the RIA approach. RIA approach is, again I am repeating, the circle starts expanding, the moment it is tangent, you report that u star values u1 star, u2 star, and that radius is basically the level of beta. So, if you look at this optimization, they are not like the primal dual problem, but you are basically trying to convert the subject to constraints as an optimization minimization problem from the PMA to the RIA, while the minimization function is transformed into subject to constraint in the RIA, which is GU is equal to 0, because the 0 point is the boundary where the feasible region and infeasible regions are demarcated. This concept which we have already discussed, but I will again discuss in more details. So, your optimization problems in the case of the probabilistic framework is like this: maximize or minimize whatever it is. So, remember this maximization and minimization I am talking about in the X space, not in the U or the reliability one, which will always be a minimization one, because you want to find the most the probable point. So, the maximization is done for f of x, which when transformed into the reliability one is basically the mean values for the function and the mean values for the probability for the parameters which are probabilistic. So, which are this? I will just mark it, and obviously for x. So, there are 3 minimum values where we start, and based on that when you do it, you find out the most probable point for P, which is the probabilistic point, or it can be for the x also, depending on how the problem formulation has been done, and you repeat from the x to the u and u to the x continuously till you are able to achieve this. So, this is for the tth iteration and this is for the tth plus 1 iteration. The mod of that should, if it is less than epsilon, you stop it. So, I will discuss few problems and the concept later on in the 57th, 58th, 59th and 60th lecture, and in the 60th lecture it will be a wrap up one, and I will continue discussing about the Soraa method, the PMA method and RIA method, and also go into the robust optimization later on in the last 4 classes. With this I will end this lecture and have a nice day, and thank you very much.